Yeah, looks like we just started the recording. Folks are still trickling in, so give it a few minutes for everyone to get in here before we kick off the presentation. But we'll be recording this and sharing it. We'll also share in the chat in a minute where you can find the recording later on. We also have some recordings of past webinars from both of our hubs shared online, so I'll send you a link to those as well. Give it like one more minute. The number is still going up. So. Okay, let's go ahead and kick off this today's presentation. We've got a very cool panel discussion coming up. Got 4 experts here on the call on biogenic carbon and novel materials. So we'll be talking about hemp, straw, fungi, and algae cement. And this is a presentation co-hosted by Carbon Leadership Forum Chicago and Nashville hubs. So I'm just introduce us real quick. I'm Emily Purcell. I'm with the Chicago hub, and then we've got Katie and Nicole on the line as well from Nashville, and a couple other folks, David Swain and the rest of our team from Chicago. So the Carbon Leadership Forum it's essentially an organization dedicated to reducing the embodied carbon in building materials and construction, transforming the building sector to really reduce the carbon footprint of the materials we build with, and even in the case of some of the materials we'll be discussing today, even storing carbon in those materials. So Carbon Leadership Forum is a hub for research, resources, collaboration, education, everything to bring folks in the industry together to get the embodied carbon emissions for buildings eventually down to 0. And then what we'll be talking about today, biogenic carbon. So I think I was just thinking before this event started, a lot of what we've talked about is generally, we're talking about embodied carbon, right? We're talking about the carbon footprint of producing steel or concrete or glass or these very carbon intensive materials, and how do we reduce that little by little. But biogenic carbon is a totally different subject. This is a carbon that's stored biologically, so in materials like plants or soil or fungi. So rather than having a positive carbon footprint that we need to reduce, these materials can have actually a negative emission. They're storing carbon throughout their lives and storing it in the building materials that we build with. So yeah, I guess just before I introduce the speakers, I'll mention that we are recording this session. We've shared links in the chat to both of our hubs, the YouTube channel for Nashville and the website for Chicago, where we will post this recording, as well as there's some recordings of past events. But yeah, let me introduce our speakers. They'll introduce themselves in a little more detail in a minute, but we have Joanne Rodriguez here from Mycocycle, Lauren Burnett from Prometheus Materials, Massey Burke with the California Straw Building Association, and then Anna Konopitskaya with Coexist Build. And I think first of all, we're going to hand it off to Joanne to get things started.
Thank you so much. You can hear me okay still?
Yeah, your audio is good.
Okay, thank you. So I'm Joanne Rodriguez, and I'm the founder and CEO of Mycocycle. We're headquartered just out of Chicago, in the suburbs of Bolingbrook, Illinois. And I want you to imagine a world without waste. If you think about the materials, particularly those in the built environment, but across all materials globally, we're resourcing less than 10% of what we've already manufactured. And so that means 90% of the materials across everything generated worldwide enters into the waste management system. In 2018, I started Mycocycle after being in an industry, construction products and building materials, that produce the fourth largest waste stream being landfilled. Since starting, we've developed locations in Mexico and Poland. We have 12 employees, patents filed, trademarks issued. I'm currently part of the Argonne National Lab Chain Reaction Innovation Fellowship Program, where we're proofing out reuse opportunities, and we've won multiple awards since starting. And what we do is we license, develop and license a patent pending process to minimize waste, create materials, and reduce greenhouse gases using mushrooms. Next slide. So a little bit about myself. I'm a former director of sustainability for a major manufacturer of building products, particularly in the commercial sector. Most of those materials are comprised of petrochemical and plastic polymers. And I knew we couldn't get our customers like federal government and colleges and universities to zero waste. So I decided to leave and embark on a journey to try to find a solution. And in taking a course in permaculture design from Oregon State University, I learned about the power of fungi and their natural ecosystem to be that of heavy hydrocarbons and petrochemicals. And so since starting, I've assembled a team of scientists and researchers. So Daniel Reyes is our VP of Research and Innovation. He has worked for over 15 years in applied mycoremediation. Mycoremediation is similar. It's using mycology, the science of fungi, to process toxins out. So it's a form of bioremediation generally used in nature. And then Colin Litto has joined us as our VP of Operations and Product Development. He came from Continuous Materials, which was purchased by Waste Management, and they are recycling municipal solid waste into roof recovery boards. And then we have support from Argonne National Lab and a very accomplished and established researcher at Jagiellonian University in Krakow for leading our EU efforts. So next slide. So the problem in general, and I know that this group knows it, but I think it's really important to point out that our landfills in the United States are 85% capacity or greater, and that the waste management industry is responsible for 16% of all man-made methane gas. To put it into context, though, what the waste streams that we're working with, the construction and demolition waste stream, there's 660 million tons of construction and demolition waste that enters the waste management system in the US alone every year. That is twice the amount of municipal solid waste, so plastic and paper. We just don't talk about it because it's really hard. And because of these methane emissions, we're seeing greater climate events. So it's a self-fulfilling prophecy that's creating human and environmental hazards worldwide. So next slide. So after taking the course in permaculture design and learning about fungi, I thought, why not try to apply it in an industrial waste stream like construction and demolition waste that also is comprised of heavy hydrocarbons. So presenting the natural ecosystem that fungi would enjoy. And we're using the mycelium, the root structure of the fungi. They're natural cleaners of our earth. They've been doing it for centuries without our help, but they're also natural builders because the chitin that makes up the cell wall of the fungi is a naturally occurring material. And those materials are water and flame resistant, insulative, and lightweight. And so it's the duality of using a nature-based solution that makes our process very efficient. So next slide. In addition to what happens in nature and what we've seen in industry, we know there's a huge body of work around mycoremediation as a form of bioremediation across multiple chemical streams and multiple waste streams. Applying them in the manner that we are is really ideal. We paid close attention to the bodies of work that were in research out there, particularly across the pollutants. And so you could see on the right that we're focused really on the polycyclic aromatic hydrocarbons. So those are like your benzenes and pyrene, and they're a known carcinogen, at least 17 of them. Heavy metal sequestration, we can't make them go away, but we can sequester them and make them less bioavailable. And then phthalates, which I'm sure many of you know are a red list chemical, we're able to neutralize that. And those are predominantly found in the petrochemical materials used in the built environment space. Next slide. So we've developed a patent pending approach that would leverage this fungal root structure to consume toxins from waste and create new bio-based raw materials. And we affectionately say that we've trained mushrooms to eat trash, and that's what we do. We have a process that is protected, wherein we're not genetically modifying in any way, shape, or form nature, but we're improving upon and really trying to harness the power and optimize what fungi can do by exposing them to different types of materials early on so they can be resilient in their growth conditions. So I'll tell you a little bit about how we do it. So next slide. At a very high level, we do a three-step process. We develop all the fungal inoculant in our lab. We're using a solid state fermentation practice. So we're generally growing across some type of agricultural input, which can also be a waste stream, to create our treatment. We take that out into the field. So we're working in situ. We could do it ex situ or establish microprocessing sites too, where we are on the footprint of waste management. So I'm really cognizant of transportation being a large part of the carbon issue. And so we want to work with a footprint that's out there already. We take in size reduced shingles, rubber, gypsum board, foam, polyurethanes, polypropylene textiles. We blend it in the second step with the materials and incubate it. So it sits for 4 weeks and processes in a controlled environment. So fungi are just like us. They like to eat, drink, breathe, and be comfortable. They're most akin, by the way, to humans, of any organism on Earth. So just think about what we like, that's what they like. And then at the end, we have a harvest, a microfiber, microfill, which is a new bio-based raw material that could go into the additive marketplace. We could actually manipulate the size of the materials and create things that could replace potentially calcium carbonate or magnesium hydroxide, going into fillers to not only replace things that we would mine that would have a high embodied carbon, but to also potentially improve the properties of the material they're going into. Next slide. So just a picture of what I described to you. Again, you see on the far left, the fungi, the entirety of that, right? We're used to seeing that mushroom cap. What we're really working with is the mycelium, which is that root structure below. We do lab cultivation. So steps 1, 2, and 3 happen in our lab. Step 4 is out in the field, and this is blended, our treatment blended with gypsum drywall. This was a 4,000 pound paid pilot that we did out in the field. Picture 5 is the field incubation. It's very passive. We did it in an intermodal container, and climate controlled, spray foamed it. It was very low tech, and at the end of 30 days, you see this massive block. So if you compare from picture 4 to picture 6, this is what happens, and this is the outcome. Then we bring materials back to our lab where we can enter post-production or secondary incubation to meet the needs of manufacturers. Next slide. So for obvious reasons, we see the benefit of driving circular supply chains and actually designing waste out of the supply chain within the built environment. We want to hit these metrics on both sides, impacting the carbon reduction on tons diverted, as well as looking at the the embodied carbon of materials that impacts 11% CO2e in the built environment space. Next slide. So to date, we've worked with multiple pilots in the field. We've scaled on over 10,000 pounds of materials since the beginning of the year across rubber, shingles, and gypsum. And we've had a very notable pilot with Lend-Lease on asphalt shingles from Fort Campbell Army Base. So we're getting very good and positive results across these really tough to tackle waste streams. Next slide. What we see the opportunity to enter into is this bio-based raw material market from waste. So not only are we reducing the carbon to develop new materials or resource extract new material, we're harnessing it and using it for our needs. Fungi like that, and so it gets stored in the materials, but this marketplace is already established. It's a $1.6 billion marketplace really focused on the consumer side. So we see consumer brands using it, but these are all of the areas that we see in the built environment side where there are opportunities to enter it in. We're already seeing acoustic products in the market in Europe as well as flooring. And as opposed to some of the early entrees into this through companies like Ecovative, where they were trying to create entire board stock materials, we're really looking at, again, the additive market where we could start to make incremental steps to embody the carbon and reduce the entire carbon cycle through the supply chain. Next slide. So since we've started, we've gained a lot of support and recognition. I'm one of the 10 finalists for the Ray of Hope Prize through the Biomimicry Institute. We just wrapped up that cohort. Pay close attention to the folks coming through there. There are a lot of new materials that I think that will be beneficial. But what we're really looking for as we move forward are more pilot and product use opportunities, and that's the phase that we're in right now. So next slide. I'm going to take you back to imagining a world without waste. There's no waste in nature. Nature has a tendency to take care of itself quite well, and we're the ones that usually disrupt her. So I think that it's very much kismet, if you will, that we're looking at nature to help solve our man-made issues. So I appreciate the opportunity to speak here. Next slide has my contact information. And I won't be able to be on for the Q&A at the very end, but certainly my email is right here. You should feel free to send any notes or any questions that you have. And Katie, I'm done.
Thank you. Thank you, Joanne. Lauren, could you share your screen?
She needs to stop sharing hers first, or I guess you do. Great, thank you. So good afternoon, everyone, or good morning. I'm Lauren Burnett. I'm the CEO and president and co-founder of Prometheus Materials. We're located just outside of Boulder, Colorado, in Longmont, Colorado. So we have developed an ultra low carbon alternative material to concrete. And that's the key thing to keep in mind here is we are not Portland cement. We are not Portland cement based concrete. We are an alternative material with very different, with a very different formulation. So as I'm sure most of you know, it's a huge problem we're addressing. Concrete's the second most used material on Earth, second only to water. 8% of CO2 emissions on the Earth come from concrete and cement, and it uses about 9% of industrial water on an annual basis. So the problem is very large and very dirty from a CO2 perspective. But it's worse than that because building stock is anticipated to double between now and 2060, which I'm sure you've all heard this statistic, but it's the equivalent of building a new New York City every month for the next 37 years. So our solution, we are producing an ultra low carbon alternative. We use microalgae, some other agents that we put into the mix, and we go through a process called biomineralization, which I'll talk about in a second. We then mix that with sand and water to create, in our case, bio-CMUs, concrete masonry units that are ultra low carbon. So biomineralization is the key to what we do here. It's a process that nature uses all the time to build seashells and coral reefs. Basically, it's using natural processes, living materials, to create minerals, and in our case, calcium carbonate. So what we do is we stimulate algae to biomineralize calcium carbonate on a commercially viable basis and time scale. So the technology started with the Department of Defense, DARPA, with 4 professors from the University of Colorado, where they were working with DARPA. DARPA wanted to see if there was a way to produce a hardened substance, such as very similar to concrete, but they knew they couldn't fly it in to the middle of, say, a desert, for instance. It's too heavy. They didn't want to truck it in over potentially hostile territory, and so they wanted to see if they could use living materials to produce something in situ. And what the professors came up with is they came up with a process of using algae and biomineralization to create a substance that was very similar to concrete. So with the success of that project, we formed the company back in March of 2021 with the 4 professors and myself, and then we completed a major pilot with Microsoft subsequent to that. So we raised a Series A round of funding in March of 2022, and we are then began actually building a company around this technology. Our partners in the Series A are pretty important to us because 3 of them are very focused on concrete in their businesses, and they all 3 came to us wanting to help them decarbonize the use of concrete and its downstream effects on CO2. So Microsoft's Climate Innovation Fund invested in us, but it's really the folks that were working with the Microsoft that are building 50 to 100 data center campuses worldwide on an annual basis. So lots of concrete. GAF Roofing and their sister company BMI over in Europe together represent the largest roofing materials company in the world, with lots of concrete roofing, particularly in Europe right now. And then Skidmore, Owens and Merrill, the architectural firm that architected the world's tallest building, the Burj Khalifa over in Dubai, One World Trade Center in New York, and many others. And so again, they know that all these companies know that they are specifying the use of massive amounts of concrete and want to change the carbon footprint of what they're doing. So from a material perspective, what we do here is what we have here is we have a very different material. The thermal conductivity of our CMUs relative to a Portland cement-based CMU is a 90% difference in thermal conductivity, which is something that is really exciting for us. We're about 15% lighter in weight, and I think most importantly for us is that we reduce CO2, embodied carbon, in traditional concrete-based CMUs by about 90%. So we're right now we're at about we're less than 10% of current CMUs. We expect to be at carbon neutral over the next 3 or 4 months, with a clear path to carbon negative. We also have a different way that we go through our curing process. Excuse me, concrete goes through about a 28-day curing process. And as I mentioned at the outset, uses about 9% of industrial water production on an annual basis. Our process is not a chemical reaction. Our process is a dehydration process where we basically evaporate the water through natural processes out of our bioconcrete over about a 7-day period. So virtually all of the water you see on the very last bottom of the slide, virtually all of the water, and I said 95% here, but we think it's probably much closer to 100, gets returned back to the earth. And as opposed to being locked into long-term building products. And from a compressive strength perspective, the ASTM minimum is 2000 for Portland cement-based CMUs. We're at about 2400 PSI for compressive strength. And actually, we've just done some internal testing on flexural strength, and we're at about 2,500 pounds per square inch on that, which is about an order of magnitude better than what you would see in normal concrete. So our vision, our go-to-market product right now are bio CMUs. That's what we're doing right now. We're going through the ASTM testing process and certification process, which will be done in this quarter. And so we believe that by the end of this quarter, we'll begin production of bio CMUs. Clearly, CMUs is a very significant building product throughout the world. There's hundreds of billions of CMUs made and used in building on an annual basis. And we've done so we've chosen CMUs based upon the fact that we can get to market very quickly with CMUs. We don't have to go through a 2-year testing process or something like that. So, our mission overall is to reduce carbon to the atmosphere by 1 gigaton per year. We're not going to do that by ourselves, and we're not going to do that next week or next year. But over time, that we believe we have the technology to be able to do that. Ultimately, we will begin to go through and go into other precast products, and then ultimately go into a ready mix concrete application downstream. So initially, we've already got ASTM sign off on non-load bearing CMUs, and we will be going through the testing process to get certified for load bearing CMUs again by the end of the quarter here. Our focus also, contrary to other companies that are trying to reduce carbon in concrete, who generally focus on the supply side, working with concrete manufacturers, we take a very different approach. We work on the demand side. So we're focused on clients that specify, like Microsoft, like SOM, to specify the use of large quantities of concrete building materials. And again, then moving on to precast applications. And ultimately, we'll be going into a ready mix application as well. Our process overall is to license our technology. We're producing right now, or we will be, but the future is really licensing our technology to cement and concrete manufacturers worldwide, as well as manufacturers of concrete products. And then again, 1 gigaton a year. And I would encourage all of you to take a look at SOM's website and go into Urban Sequoia. It's fascinating what they plan to do with buildings, and they look at Prometheus materials as a key component of their Urban Sequoia strategy. Lots of press over the last several months. This area is hot and getting hotter, and we're very excited about our opportunity to work with companies and as well as folks like yourselves to reduce embodied carbon. So thank you very much.
Thank you, Lauren. That was great. Nancy, you're up next.
All right. Hi, everyone. My name is Massey Burke, and I'm the co-director of the California Straw Building Association. And I'm going to talk a bit about not a product, but a community. So building with straw is what I would currently call an open source, mostly a nonprofit building community made up of, I'll keep going, here we go, California Straw Building Association, trade organization, nonprofits, that's made up of architects, engineers, contractors, DIY, all practicing and helping to scale various ways to use straw as a building material. Some of the stuff we're working on right now, working on an LCA for straw. These exist. There's a couple of European ones. We don't currently have an American LCA for straw, and then straw-based products, which I'll talk a little more about in a minute. Working on scaling up the workforce skills for building with straw and other natural materials. Working on supply chains and also looking at land management and supply chains and what impact that has. Working on code and testing. California Straw Building Association was responsible for writing the international straw building code that currently exists in the residential code. And we do ongoing code work in various ways. Professional education, more training resources, online trainings, and working on issues like insurance, helping other parts of the sector become just familiar with and comfortable with straw as a building material. Okay, so straw anatomy 101. This is something that you all are probably familiar with, but straw is the stalk of one of the most common grain growing grasses, cereal producing grasses. So typically in California, we build a lot with rice straw, but you can build with wheat straw or oat straw, barley straw. And what's important about this is that straw is what is left over when you harvest the seed off the top of the plant. So straw is a good building material because it's mostly silicon and carbon, and all the nitrogen is harvested as the food from the cereal. So it doesn't really break down very easily unless you get it wet and keep it wet, as with any cellulose-based building material. This is actually also important because it explains the carbon storing mechanism of straw. Plants photosynthesize, and what that means, especially annual plants, is that they remove atmospheric carbon and turn it into plant material. And as long as that carbon stays locked up in the plant material, then you have stored the carbon, you've removed the carbon from the atmosphere. In normal circumstances, straw will decompose in about a year in the field, a couple of years, and re-release that carbon to the atmosphere. But if you take the straw and put it in a building where the whole point is for it not to decompose, then that carbon is essentially locked up. So we're leveraging the natural behavior of plants to store carbon in the built environment. And the nice thing about straw is that it does it on an annual basis rather than a multi-year basis, as with wood. Couple notes on sourcing straw and growing straw. We currently talk about straw as a byproduct or a waste product, which is, I'm sort of taking a both and approach to thinking about straw supply chains right now, but it's, as you're probably aware, land management processes are becoming more and more important when considering carbon footprint of building materials. And so one thing I like to work on is thinking about that and also thinking ahead for how to support climate smart or regenerative land management processes as much as possible. So one reason we have a lot of straw available right now is that straw producing plants are grown as a monoculture, which means that it can be hard to absorb, hard for that cropland to reabsorb all of the straw into the soil in the planting cycles that are typically used. And so you have, especially with rice, again in California, but also for large scale wheat growing and other things, you just have a lot of basically leftover straw stalks, a lot of which get used for animal bedding or irrigation control, but there's still a good bit left over from that. in a more climate smart or regenerative farming process, there's not really any such thing as a waste product. So any biomass is going to be fed back into the soil. And so if you're trying to produce an annual plant like straw in a way that is climate smart, then you're going to be, it's purpose grown in a sense. You're always designing for what biomass is coming into and going out of your system. So it's just something that I find very interesting to be aware of as we continue to improve our climate impact as materials. Yeah, quick note on straw production and soil health. You can design straw production into a farming practice that employs good soil management, which really means just helping soil microbiome diversity, which means that the farming system can store carbon in the soil. So we have this sort of 2-for-1 benefit of straw and other plants, where if your sourcing is climate aware, then you can store carbon both in the soil as a part of growing straw and in the building as a part of using produced plant carbon in a place like a building's wall where it won't break down. This is kind of fun. If you're not aware of soil carbon storage, I'm sure you've probably heard of this because people are more and more excited about the potential of agriculture to respond to climate change. But Gabe Brown is one of the early regenerative farmers in North Dakota. He grows wheat and a bunch of other things. And this chart just tracks his soil carbon storage over time. And the way the chart is set up is by technique that he employed for climate smart agriculture. And so he began no-till, and that began to help grow his carbon storage in his soil, added crop diversity, added more cover crops, added more diverse cover crops, and then finally integrated grazing, which, if employed appropriately, really helps to stimulate soil microbiome processes that store soil carbon. And so you can see that blue dotted line essentially just goes through the roof over, let's see, what is that, a 20-year period. Okay, so how to build with straw. Typically straw is currently site built and usually pretty simple. One of the advantages of straw as a building material is that you don't have to do a whole lot to it. You can harvest it, needs to be below 20% moisture content, bale it up, and essentially stack the bales in the wall. Bales can be integrated with framing. They can be load bearing, though you end up with more design limitations when you build with straw that way. And the bales can be modified in various ways to accommodate different types of frames, but simple to field modify, usually cut with a chainsaw, or sometimes custom bale cutting tools, stacked with a crew or with a community. There's a related technique called light straw clay, where you can form a straw wall in a frame, again, site built. And both of these techniques have, ancient roots in European timber frame building, other types of infill building. So this is really just the modern form of a traditional technique. We are starting to see prefab straw panels. The picture on the right is a company called EcoCocoon, and other panelized straw systems are starting to come into existence. And then various other types of straw products. On the lower right is a product called Stack Block, which is in development. Compressed straw blocks. There's MDF board being developed out of straw, and other beginning. I would say we're a very incipient field for developing straw-based building materials, and we have this really pretty robust open source community that can act as the foundation for more product development. What straw usually looks like finished is a plaster. You can finish straw conventionally with sheetrock, but it's currently more typical to do a lime or a clay plaster on the interior. Lime, sometimes clay, often conventional siding on the exterior. And then one more note on products. This is a project that I'm currently involved in, very early stage. It's an American panelized wall system, so similar to EcoCocoon in the previous slide, but a lot of the current panelized straw systems are still really wide. because the accepted R value per inch of straw is probably lower than its actual performance R value. And so panelized wall systems, I think the thinnest one right now is 8 inches, and they tend to be more like a foot thick or thicker. And so we're working on one that is going to be more conventional framing thickness, so a 5.5 inch thick panel. And it's a SIPS panel essentially, but we're modifying the straw just enough to increase the R value per inch, which allows us to make a fairly thin, fairly light straw insulated panel that's carbon storing. And again, this is a chart that I'm sure you've seen before, but the comparative embodied carbon of various building materials. On the left, conventional or mineralized building materials obviously have a lot of embodied carbon associated with them. And as you get over toward the right, the plant-based building materials have quite a lot of carbon storage potential. I believe the figure for straw, 1 kilogram of straw stores 1.67 kilograms of atmospheric carbon. So straw is one of the highest plant-based carbon storing building materials. Some comparisons from some modeling that a colleague of mine did. Typical 1,200 square foot house, and these are, he modeled these in, this is for Vermont actually. So embodied and operational carbon to 2050. Typical 1,200 square foot house would be about 84 tons emitted. Conventional materials, reasonably, but not particularly operationally efficient house. Energy efficient version built with natural materials such as straw is going to sequester close to 9 tons of CO2. And then just things that we need to do for carbon and straw, as I mentioned, working on a straw LCA EPD. And I'm kind of in the middle of this, and so we're working with Katie actually, and so we're working on questions of whether we need to create a new PCR, blah, blah, blah. So really in the weeds with that. Partnering with other organizations who work with biogenic materials for the LCA EPD process. Working on including data that we currently have into databases, and again, studying supply chains. Thank you, that's it for me.
Awesome, thank you, Massey. And then last but not least, we have Anna. Why don't you go ahead and share your screen?
Good morning. Thank you for having me. My name is Anna Konopetskaya, and I'm a CEO and co-founder of Coexist. At Coexist, we design with regenerative materials and we manufacture those regenerative materials. So I'll start by why it is that we do this. UN published a report. They do this, I think, every year or so. And they stated that a city the size of New York City pretty much is built once a month across the world, and it's going to continue so for the next 40 years. While we can't stop this kind of construction, massive construction, we can actually, if we make a change in how those buildings are built, collectively, we can create a huge impact on our environment. Why is it important? Because construction industry is responsible for huge amounts of energy consumption and emissions, about 40% comparing to other sectors. And when we talk about carbon emissions, we're talking about embodied carbon and operational carbon. Embodied is something that happens during the construction of a building, and operational is during the life cycle of a building to maintain it at the optimum levels, the building. This is a diagram that shows concrete, steel, and aluminum. We all heard about these numbers and building operations, but what I find interesting is that not many people look at this number here, which also includes building finishes, glass equipment, and plastics and rubber and paper that also goes into buildings. So while the number usually that's circulating around is 40%, it may be possible that it's actually even over 50% of CO2 emissions that the building industry as a sector contributes to the global warming and atmosphere. So if we want to tackle this problem, we have two ways to do this. One is we lower the embodied energy, which is the energy you need to build a building. And two, we make buildings efficient so that we lower the operational energy of those buildings. And if we look at the an example of materials, let's say in the building envelope, such as insulation, we see that petrochemical products like polystyrene or spray foam, they're the worst offenders. The bad insulation is not so bad, but still not that great. And then you have natural materials, with the straw bale being the best. And it seems like nothing can beat the straw bale. But this presentation is about hempcrete. That's something we specialize in, which also shows really nice numbers of carbon sequestration. So what exactly is hempcrete or hemp lime, like some people say it? Basically, it's made out of, excuse me, the woody stalk of the plant, the hemp, lime-based binder, and lime is one of the most naturally occurring, one of the most available nutrient minerals out there, and water. There's nothing new about this product, this material. It actually goes back to the 6th century, found in France. It was found in the 7th century in Japan. Then it was kind of rediscovered or renewed or republicized in France about 40 years ago. And since then it became a very popular product across Europe, between Italy and Ireland. And now it's picking up speed in the US. These are some of the older projects. There are a lot of projects now going on that have not been published, let's say. And this is what it looks like on the inside. So basically, in these walls, there are 3 products. It's a structure, usually wood structure, hempcrete, could be block or a different kind of application, and a plaster on both sides. Actually looks really beautiful, not to mention the other benefits of the product. If we look at the conventional building assembly, we will see that a lot of times it's it's built out of basically petroleum-based materials, plastic materials. Even if we talk about things like curtains or even our clothing, if it's synthetic, it's made out of some kind of petroleum products. And the whole goal of this kind of assembly is to block any kind of air infiltration or moisture vapor movement between indoor and outdoor. And while it works, the problem with this kind of construction is that it either emits some kind of off-gassing inside of our space, or it traps it inside. The way hempcrete works is completely different. It actually is not a cavity wall like in this picture with a mouse inside, but it's actually a solid wall. And the principle of it is same as wool product. The particles of air are trapped inside, and then they insulate the wall with those particles of air. It is a breathable system, and it allows the passing of moisture vapor because this material dries out, but it emits this moisture in the driest area, so the house where you need it. The way to install it is you can install it by hand, or you can spray it, or you can install the blocks. These are coexist blocks on this picture. We're the first company in the country to actually produce it at a factory. This is the same corner of the project. We installed the block first, and then it was sprayed here. This gentleman from Pennsylvania as well, I forgot to mention we're out of Pennsylvania. Cameron of Emery Chandler is spraying that pocket that was blocked from the outside, but really the block went inside first because it's already cured, and the work could continue on the inside and the finishing work as well. And he sprayed it on exterior, and that could dry for the next 2 months. On this slide here on the bottom, you see materials that you probably recognize. You see all of them, if not all of them, most of them in conventional construction. They're really terrible products that not healthy to manufacture, first of all. And second, as I mentioned, they either off-gas or they trap those gases inside. Nothing is natural about them. And then the benefits of hempcrete you see above it. Does not burn. We don't use chemicals. You just don't need chemicals for that kind of product, not to grow, not to manufacture. It helps you regulate temperature and humidity of the house, so it lowers the energy consumption of the space. And among other benefits, it actually continues to purify the air. And I'll get to that a little later as well. This is a research was done on carbon sequestration. I won't go into details, but they studied the distance for transportation for hemp and binder to the manufacturing facility. In this diagram, the black lines show the greenhouse gas emissions, and green, orange, and yellow is the carbon sequestration. And it shows that no matter how far your field is, how far, well, not no matter, within limits, of course, but if it's, let's say, 2 hours away from the factory, hempcrete production still sequesters more than the machinery emits into the atmosphere. And usually people ask, well, what about all that equipment like tractors in the field or factory running full speed? Wouldn't that make it, wouldn't that raise the carbon footprint? Wouldn't it make it carbon positive? No, the research that's been done shows that even with all the equipment involved, making the blocks at a factory still produces carbon negative product. So how does it do that? It sequesters carbon, most of it during the growth cycle of hemp, which is very short, it's 3-4 months. And then the rest of sequestration happens during the carbonization process. Once it's installed in the house, that process could take up to 200 years, during which it basically turns into limestone. And by doing that, by sequestering carbon out of the atmosphere while it's curing, it actually purifies our air as well. And someone mentioned before me farming practices. We work with Rodale Institute, and we follow closely the research in farming practices. They actually pioneered the word organic. So, excuse me. So they're pretty far advanced in the research, and the no-till practices that they advocate in regenerative farming practices also reduce CO2 emissions back into the atmosphere. Some tests have been done on the hempcrete blocks. They do not grow mold, no matter how much moisture there is. It does not burn. This is a test that was done on a scale from between 0 and 400. The flame spread is 0, just does not burn. The acoustic qualities are excellent. And one of the most important things to mention is that it's a new product, but it was just accepted into the International Residential Building Code. It will be adopted in 2024 version, which is a great news for all of us. Coexist actually co-signed the application. This is great news because it will also pave the way for having it approved for commercial buildings, building code. And in conjunction with that, heavy timber was also approved to replace steel structures in the buildings, which also further will reduce carbon emissions in our buildings. And a couple of things that we're working on. So air quality, we're actually testing. There are not many tests that actually prove that the air quality is superior inside. There is one building that was just completed in Pennsylvania as well by Dunn Enterprise. It was a affordable housing retrofit. It was completed this summer, and in partnership with the university, they tested the air. And I believe that the tests were just completed. We were promised that we'll see the results of it very soon. And the image in the middle is something that we built. This is a building kit that this is our first one that we constructed, and we're going to test the quality of the air for the next 2 years. The goal of this little structure is to show, demonstrate actually how we can remove petroleum-based products out of our structure. There are almost none of them there. It's pretty much impossible to remove all of them because wires are enclosed in plastic, let's say, and conduits are plastic as well, but we tried our best to remove almost everything. We even created our own plastic covers out of compostable hemp plastic. We made an outlet cover, and the mycelium sound panels we also created. We didn't use it in this structure, but it's something we have created in the past and used in our other structures. Just a little bit about ourselves. We started out by making a little demo unit on wheels that we took across Eastern US, including Javits Center in New York City. We're the first company and only company right now to manufacture blocks at a factory. We've done all kinds of testing on the blocks in real life projects, including this one in Hudson Valley, New York, where hempcrete was sprayed against it. And then to take it into the mainstream, we created these kits that were sold out within the first 6 months. And this is just a little bit about us, who we work with and where we've been published. This needs to be updated. We've been published across the world in architecture, design, and other publications. And we work with private companies and government to fund our research. That's it. Thank you very much. Thank you for listening.
Thank you so much, Anna, and everyone else. These are awesome presentations. I really liked seeing the connection between this embodied carbon savings, like not just savings, but real transformation of how we build. The intersection between that and health and wellness of the inhabitants of these buildings, and also just the beauty and design that you're finding in these materials. That's it's always great to see that connection of all of your products. I think, let's see, we have about 5 minutes left. There are a couple questions in the chat. I think, let's see, I saw that a couple questions like about where you all were coming from. So one about the R value range of straw and where could that be used in different climates, and then also about your location of that house in Pennsylvania. I guess maybe just kind of bring those together. How have you all been working as far as like we're located all over the US here, and worldwide as well for I saw some of Joanne's other locations, but how are you all bringing together, like working with your native and local materials where you're at, and kind of bringing that together and scaling up to go nationwide? So, Massey, do you want to maybe take that on and address the the R value and using straw in other climates?
Yeah, I wasn't quite sure who that question was addressed to. Yeah, so R value for straw is typically in the code for baled straw is R2 per inch, more or less depending on which way you orient the bale. So flat or vertically matters. We're going to shoot for getting up closer to 4 per inch with the panelized product that I mentioned to you. And the stack block, which is another one of the products that I showed, has preliminary thermal testing that's getting them close to R4 per inch as well. So kind of, in the range of like wood fiber board insulation. What was the other question? Oh, scaling up localized materials.
Yeah, I was just thinking like these are all kind of local materials to where you all are located, but yeah, how are you bringing that to a national level?
I mean, I think for straw product development, straw is ubiquitous in the United States. I talked a lot about rice straw because we have it in California, but there are very few states that don't have straw producing agricultural sectors. So it's more what is the right way to scale. And I'm a big fan of I mean, I think we're all trying to define what bioregional supply chains and what's the definition of a bioregion when you're talking about scaling up building. So I don't have a good answer to that. I'm in the middle of thinking about it, but I think you sort of bioregionally replicating models that are adapted to locales to some degree is probably the right way to scale up. It doesn't mean that you can't have one national company, but I think the structure of that company would still be bioregionally attuned, I guess you could say. I feel like I have one more thought there, but I'll leave it at that.
I'll add to that as well. That's it's always a question on the minds of people who start businesses. How do you scale? How do you take it into the mass mainstream? That was one of the biggest things for us because we're fighting with the market we're in has so many roadblocks, and one of them was actually to let people know that it's available and change the maybe habits of the trades. And so one of the things that we did was we approached the media. We also created a product that can be affordable and maybe built by people themselves instead of relying on expensive construction labor. And so that allowed us to kind of to pick interest of public. And so that kind of started it. And we basically just used media for this and just keep pushing. And I think one of the great ideas that was mentioned earlier was to contact clients who build at scale certain projects where you want to replace material and then work with them.
I guess as maybe a final question, I remember from Joanne's presentation, I kind of wrote down a line that she said about we're trying to design waste out of the process. There's no waste in nature. And that kind of stuck out to me. David and I at CLF Chicago, we're both work for architecture firms. And I think, looking at the design profession, I know we're not really thinking that way yet. So what's a good takeaway for folks who are designing buildings or clients who are looking to develop buildings? How do we build the use of some of these products into our design thinking? What do you need from us to take the next step?
Good question. I think that the architects, I'm an architect myself, licensed architect actually, it's a very good question. I see a lot of disbelief in the architecture community. I see very low interest in architecture community, I think it's literally just a matter of reaching out, doing these kind of presentations, talking more to architecture community, and just bringing the sample, put it in their hands and say, and giving them the specs and saying, listen, this is it's a viable alternative. But also, of course, needs to be adopted by trades who are resistant to change. Anyway, it's a very complicated, very good question. So anyway, I think it's at the moment right now is just speaking more and just letting them know that there's an option out there.
And just to add to that, I would say if you really get serious about forefronting carbon and carbon storage in your designs, then you're not going to be able to help supporting these materials, because what you pull together a great panel, and these are the materials that are pretty hard to beat in terms of climate action. And so I think that would just in and of itself would go really far.
Yeah, that's a great point. Just nothing is creating as drastic a change as some of the materials we're just talking about today.
Yeah.
So, all right, well, we're just at noon, so we can let folks go. But if anyone's got any last questions, thank you so much to the speakers. It's been great learning about everything you're working on. It seems like there's just things are changing so fast right now, and it's awesome to hear from folks who are at the forefront of that. So thank you so much.
Thank you.